Hi everyone, welcome to CS 188 section 8, and today we'll be going over the worksheet solutions. So our first problem is on sampling. So the problem says that we would like to analyze people's ice cream eating habits on sunny and rainy days. Now suppose we consider the weather along with a person's ice cream eating over the span of 2 days. We'll have 4 random variables, W1 and W2, stand for the weather on days 1 and 2, which can either be rainy R or sunny S, and the variables I1 and I2 represent whether or not the person ate ice cream on days 1 and 2. And take values T for truly eating ice cream or F. We can model this as the following Bayes net with these probabilities. So we see that ice cream depends only on the current weather. So now they say, suppose we produce the following samples of W1, I1, W2, I2 from the Bayes net. So according to these local conditional probability tables, they draw these samples. So in the first problem, they ask us, what is the probability that W2 equals R? So what we do is we look at all our samples and we count how many of them have W2 equals R. And that's 1, 2, 3, 4, 5. So 5. And how many samples are there? A total of 10. So the probability is 1/2. Okay, so for number 2, they say cross off samples rejected by rejection sampling if we're computing probability of W2 given I1 equals T and I2 equals F. So we look at our samples and we cross off all of them that are not consistent with the evidence. So we need I1 equals T and F. So this is not T and F, 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 does have T and F, does have T and F, not T and F. So only 2 samples are left after we do rejection sampling. So now we notice that rejection sampling seems to be wasting a lot of effort, so we decide to switch to likelihood weighting. Now they say, assume we generate the following 6 samples, given the evidence I1 equals T and I2 equals F. They want to know what is the weight of STRF. So the weight is the multiplication of all the probabilities of the evidence given the parents. So it's the probability of I1 equals T given W1 equals S times the probability of I2, which is evidence, equals F, given its parents, which is W2 equals R. So if we look at our tables above, we find this is 0.9 times 0.8, so we get 0.72 is the weight. Now they ask us, use likelihood weighting to estimate probability of W2 given I1 equals T and I2 equals F. So what we need to do is find out the weights for all of the 6 samples that we drew. So we already calculated the first sample, which was 0.72. Now for the second one, I won't write out the 2 probabilities we multiply, but I'll jump straight to it. So it's T given R. So T given R is 0.2 times F given R, which is 0.8. So this is 0.16. Now W3 is right here, T given S, which is 0.9, times F given R, which is 0.8. So that's 0.72. Now the next way, W4 equals T given S, which is 0.9, times F given S, which is 0.1. So that's 0.09. And we notice that W5 is the exact same as W4. So that's going to also be 0.09. Now we have W6, which is T given R. So that's 0.2 times F given S, which is 0.1. That's 0.02. Okay, so now we have all the weights. So we can go ahead and calculate the probability that W2 equals R. Given our evidence, I1 equals T and I2 equals F. So for all the samples, on top, we sum them, all the weights that match W2 equals R. So W2 equals R is 1, 2, 3, the first three. So we get 0.72 plus 0.16 plus 0.72. And we divide by the sum of all the weights. So 0.72 and if you calculate this out, you'll get 0.889. And if you want to do the probability of W2 equals sunny, S, then it's just 1 minus this value. Okay, so now let's move on to the next problem, which is on decision networks and VPI. So the problem says that a used car buyer can decide to carry out various tests with various costs, and then, depending on the outcome of the tests, can decide which car to buy. We'll assume that the buyer is deciding whether to buy car C, and that there is time to carry out at most one test, which costs $50, and which can help to figure out the quality of the car. A car can be in good shape, of good quality, Q equals plus Q, or in bad shape, Q equals not Q. And the test might help to indicate what shape the car is in. There are only two outcomes for the test: pass and fail. Car C costs $1,500, and its market value is $2,000 if it is in good shape, and if not, $700 in repair will be needed to make it in good shape. The buyer estimates that C has a 70% chance of being in good shape. So the decision network is shown below. So the utility depends on what action do I take by the car and the quality, and the test depends on the quality of the car. So first, it asks us to calculate the expected net gain from buying the car C, given that there's no test. So we can say that the expected utility of buying equals the probability that it's in good shape plus Q times the utility of it being in good shape and buying plus the probability that it's in bad shape, not Q, times the utility of it being in bad shape and buying. So from the information given, the probability it's in good shape is 0.7, and the utility we get is then we're able to sell it for $2,000, but it costs us $1,500 to buy. Now the probability it's in bad condition is 0.3, and the utility is we can sell it again for $2,000, and it cost us $1,500 to buy it, but it also costs us another $700 to repair it. So if we calculate this out, we get the expected utility is 290. So this was just applying the expected utility formula, which was in the lecture previously. So now in 2, they say tests can be described by the probability that the car will pass or fail the test given that the car is in good or bad shape. So we have the following information: the probability that it passes given it's in good shape, and the probability it passes given it's in bad shape. Now they ask us to calculate the probability that the car will pass or fail its test, and the probability that it's in good or bad shape given each possible outcome. So first, let's do the probability the car will pass. So the probability that it'll pass is we marginalize. So we write this as the joint of t equals pass and q equals some q value, which we're summing over. So we can write this as the probability t equals pass given q equals plus q times the probability that q equals plus q. So this is just the chain rule plus the probability that t equals pass given q equals not q times the probability of q equals not q. So if we fill this in, the probability t equals pass given q equals plus q is 0.9. The probability q equals plus q is 0.7 plus t equals pass given not q, it told us 0.2. And the probability it's in bad shape is 0.3. So this is 0.69. This also tells us the probability t equals fail is 1 minus probability t equals pass, so it's 0.31. Okay, so now that we have this information, they want us to calculate the probability that is in good or bad shape given each possible test outcome. So from this, we can calculate the probability that it's in good shape given it passed the test. And we're going to apply Bayes' rule so we can flip everything. So t equals pass given q equals plus q times the probability q equals plus q divided by the probability t equals pass. And we know all these values. T equals pass given q equals plus q is 0.9. The probability of q equals plus q is 0.7. And we just calculated the probability of t equals pass, which is 0.69. You can also do the same for the probability it's in good condition given it actually failed the test. So we can rewrite this using Bayes' rule again. So filling in these values, we get probability t equals fail given q equals plus q. So that's 0.1. The probability it's in good condition is 0.7. And the probability it fails is 0.3. Okay, so now let's move on to number 3. Calculate the optimal decisions given either a pass or a fail and their expected utilities. So first we can calculate the expected utility of buying given that I passed the test. So this is going to be the probability that the car is in good condition given that I passed times the utility u of it being in good condition in buying plus the probability that it's in bad condition given t equals pass times the utility of it being in bad condition, not q, and buying. So we know these probabilities from the previous part, from part 2. So it's going to be 0.9 times the utility of plus Q in buying, which we did before. It's 2,000 minus 1,500 plus the utility of, or the probability of minus not Q given pass, which we calculated before, was 0. Sorry, this should be 0.09 times 2,000 minus 1,500 minus 700. So that equals about 437. So now we can actually do the exact same thing for the expected utility of buying given t equals fail. So it'll be the same thing. It'll be the probability of Q equals plus Q given I failed times the utility of it being in good shape and I buy it, plus the probability it's in not good shape given it failed times the utility of it being not in good shape in buying. So using the result, the probabilities from part 2, this turns out to be 0.22 times the utility is still 500 plus the probability here is 0.78 times the utility, which is the same as the previous part, is minus 200, so that equals minus 46. They also ask us to calculate for all decisions. So another decision is the expected utility of not buying, given it actually doesn't matter because if we don't buy, then we get 0 utility. So now we know that the maximum expected utility of the test passing is 437 if I buy, and the maximum expected utility if I fail, well, I have two options. I can either get minus 46 if I buy, or I can get 0 if I don't buy. So I'd rather take 0. So those are my MEUs. So now they want us to do, what is the value of perfect information of the test should the buyer pay for a test? So we want to know the VPI of test T. So the equation for VPI is we consider all possible values of the test, the probability of that test outcome times the maximum expected utility of that outcome minus the maximum expected utility if I didn't get any more information. So given the evidence I already know, which is actually none in this case. So in this case, we know the probability that t equals pass is 0.69, and the maximum utility from the previous part was 437, plus the probability that it failed was 0.31 times the maximum expected utility of it failing, which actually turned out not to buy, which meant I got 0, minus the maximum expected utility if I didn't know any of this information, which from the previous part, which from actually part 1 up here, we calculated to be 290. So this turns out to be around 11.53. So that's the value of perfect information for knowing T. But they say the test costs $50. But the amount of information I get is, the value is actually $11.53. Therefore, we don't want to pay for the test because that information is not worth it. And that's it.